Good day, ladies and gentlemen. You are welcome to our lecture number 6 on power electronics. Mcen508. My name is Kabir Ahmad Abu Bilal, and today we'll be looking at IGBT, that is insulated gate bipolar transistor. This is just like other transistors, or like MOSFET rather, because it is a voltage control device, meaning it is the voltage that is applied to the gate that controls its operation, and it also has a high input impedance, just like the MOSFET we have discussed, and it has low on-state conduction losses. That is, whenever it is in conducting mode, the losses are very small, like in the BJT. And its construction is very similar to that of the MOSFETs. The only difference is that the N layer, which is at the drain in the MOSFETs, is now replaced with a P substrate, and we call that substrate now a collector. As you can see from this diagram, it is a three-terminal device. We have the collector here, we have our emitter, while we have the gates which control the flow of charges from the collector to the emitter. Well, we need to just look at this and compare it with the MOSFET and BJT. You know, in BJT we have gates, we have drain and source, while that is in MOSFET rather. In BJT we have collector, emitter and the base, but this one you can see it has like a combination of the features of the two. It has collector and emitter just like in the BJT, and it has gates just like in the MOSFETs. And this is the symbol. As we know, whenever the arrow is pointing out, it means it is N channel. And this IGBT, as I've already mentioned, it has three terminals mentioned here. Whenever the collector and the gate voltage are made positive with respect to the emitter, your device is in what we call the forward blocking mode, which means it is forward biased, but it is not conducting because there is no control gate voltage that will enable it to start conducting. Now, whenever the gate to emitter voltage becomes greater than the threshold, that's the minimum voltage for it to start conducting, the IGBT will now be in the forward bias mode, and it will be an N-channel type with the P region, as we have explained just now. Now, whenever this happens, that is when we make the gate to emitter voltage greater than the minimum threshold, the device will now be in forward conducting states. And whenever it is in this forward conducting states, the P substrate will now inject holes into the epitaxial N layer. We have seen three methods of designing these components. We have diffusion methods, we have alloying methods, and we have epitaxial growth methods. I have already discussed them in my first lecture. Whenever there is an increase in the collector to emitter voltage, that is the VCE, this will result in the increase in the injected number of holes, and finally it will produce a forward current, which will now enable the device to be producing the output control for controlling the device connected to it. The characteristic curve of the IGBT is given here. This is the circuit. As we can see here, it is in common emitter configuration because the emitter is connected to both input and the output. And this is our plot, which is giving us the output parameters, the collector current with respect to the VCE, that is the voltage between the emitter and the collector. And the controlling voltage is the voltage between the gate and the emitter. As we have seen, whenever the VGE becomes above the minimum threshold, that is this lower line, you find that it will start conducting. But whenever it is below that value, it will be in the cutoff region and no conduction. As you increase the value of the VGE, you'll find that the height of these your curves are increasing, and of course the current output will also be increasing. There is another plot, that is a plot between the collector current, which is the output current, and the voltage between the gate and the emitter, which is the controlling voltage I have just discussed here. So we have a plot between IC and VGE here, and for a given value of VCE, meaning the VCE is now the constant, while these are the variable parameters, the IC and the VGE. And we call this curve the transfer characteristic. And the controlling parameter, as I've already mentioned, is the voltage which is applied between the gate and the emitter. And whenever this VGE is less than the threshold, the IGBT will be in off state, that is, it is not conducting. But whenever this one becomes greater than the threshold, then our IGBT will be in conduction state. And this IGBT is used in applications where we need medium power, such as AC and DC motor drives, like in power supplies and in solid state relays. Of course, we are going to see other applications of IGBT. Now, the switching characteristic, which give us the relationship between the voltage applied between the gate and the emitter, which is the controlling voltage, the output voltage, which is the VCE, the voltage between the emitter and the collector, and the output current, which is the IC. So as we can see from this diagram, whenever our VGE starts rising from its minimum value, you find that our VCE is already at its peak value, but the device is not conducting because the controlling voltage is low. So whenever you reach the threshold value, that is the minimum value of the gate emitter voltage, you find that the value of your VCE, which initially was high, will start falling, because whenever it is in conducting state, it requires a very small voltage between the emitter and the collector. So the time it will take from 0 to reach that minimum is what we call our turn-on delay, and from there to reach 90% of the maximum value is what we call the rise time. So after that, we reach the maximum value and it will remain steady, and in that state you find that your VCE will remain very small, because when it is conducting, the voltage between the emitter and the collector is very small. We don't need much. So after that, whenever it starts falling from that maximum value to the threshold value, you find that your VCE will now start rising. And from that threshold value down to the lowest value, you find that our VCE will now rise to its maximum value. But the corresponding current, which is the output current, is following the curve of the controlling voltage, that's the voltage between the gate and the emitter. Whenever the voltage between the gate and emitter increases, the current will also start rising. It will reach 10% of its value, and that is where we have our rise delay time. And from that 10% to 90% is what we call our rise time. And after it reaches maximum value, it will remain in as much as our controlling voltage, that is the voltage between the gate and the emitter, is at its steady value. So the moment it starts falling, the same thing will happen to the current. It will start falling. It will start falling from the maximum to 90% of its maximum value, and that is our turn-off delay time. And the time it will take to reduce from 90% to 10% of its maximum value is what we call our fall time. This is just explanation of what I have already mentioned. We said the turn-on delay is the time which is required for this current, that is the ICE, to rise from 10% of its maximum value to the peak value, which is the IC. So the time from 0 to 10% is what we call the delay time during turn on. And the rise time, it will be the time to rise from that 10% to its maximum value, which is IC. And after turning on the device, you find that the VCE will be very small. I have already explained this. Whenever you are in steady state conduction, you find that it requires very small voltage between the collector and the emitter. During the turn off period, we have two times. We have the turn off delay and we have the fall time. And the time delay that is required for the current to fall from the maximum to 90% is what we call the turn off delay. And the VGE will now fall from the threshold value to the point where the device will stop conducting. Now, during the fall time, the collector current will fall from the maximum value to 90, from 90% to 10%. And of course, the time interval between the collector and emitter voltage, it will rise to the maximum value. It depends on the range of time taken from 90% to 10%. And this IGBT, they are found to be faster in operation than bipolar junction transistors, but they are slower. That is, MOSFET are faster than them, but they are faster than the BJT. And the IGBT also, it has a superior drive. That is, whenever you want to drive a heavy machine, the power electronic circuit normally use IGBT, and it has very good output characteristics when you compare it with the bipolar junction transistor. And also the IGBT, they are very suitable for high voltage application, for high current application, and they can operate at a frequency of up to 20 kilohertz. And they are available in 1400 volt 600 amperes or 1200 volt 1000 amperes, depending on the application for which it is going to be used. And the other areas of applications, we have mentioned few before. They include the medium power applications like AC and DC motor drives. They have been mentioned before. They are also used in medium power supplies. They are used in solid state relays and contactors. They are used in general purpose inverter and the UPS. They are also used in welding equipment. They are used in operating servo machines, that is in servo controls. They are used in robotics. They are used in cutting tools and induction heating. And the typical rating of the IGBT I have mentioned before. The voltage can be 1004 and the current 600 amperes, or 1002, 1000 amperes, as we have seen before. And the maximum operating frequency, as mentioned, is 20 kilohertz, and the switching time is as low as 2.3 microsecond. And the on-state resistance, that is when it is conducting, the resistance is as low as 600 milliohm. So ladies and gentlemen, this is the end of this lecture number 6. As usual, try to watch it over and over again till we meet in our lecture number 7. Thank you very much.